Every AI model you've used was trained. That word sounds straightforward. An AI system learns from data, the way a student learns from a textbook. But the actual mechanism behind training is nothing like how a person learns. It's mechanical, it's mathematical, and understanding it changes how you think about what these systems actually are and what they can't be. Start with what a language model actually is before training begins. At its core, it's a mathematical function, a very large one, with billions of adjustable numbers called parameters or weights. Before training, those numbers are set randomly. Feed the model a question, and it produces random output. The weights don't mean anything yet. The goal of training is to find values for those billions of numbers such that the function reliably produces useful outputs. That sounds simple. The machinery for getting there is what's interesting. Training works in a loop. You feed the model an input, a sentence, a paragraph, a piece of code, and it produces a prediction. For a language model, that prediction is usually what word comes next. You then compare what the model predicted to what actually came next in the training data. The gap between prediction and reality is called the loss. A large loss means the model was badly wrong. A small loss means it was close. The key step happens next. A mathematical process called backpropagation traces backwards through the model to figure out which weights contributed most to that error. Then each of those weights is adjusted, slightly, in the direction that would have made the loss smaller. This is gradient descent, a slow mechanical walk downhill toward better predictions. Now repeat that loop, do it 1 trillion times, on thousands of pieces of hardware running in parallel for weeks or months. That is what training is. Each individual step is tiny. The cumulative effect of trillions of steps over enough data is a model that has encoded something about how language works, what facts co-occur, how arguments are structured. It's worth being precise about what tiny means here. The adjustment to any single weight during one step is a fraction of a fraction, a number so small it would be meaningless in isolation. The model has no concept of what it's doing. It doesn't understand what a word is, what a sentence means, or what a fact represents. It's purely responding to numerical error signals. This is what makes the end result feel almost paradoxical. Behavior that looks deliberate and knowledgeable, produced by a process that contains no deliberation and no knowledge. Only arithmetic, repeated at scale. The scale involved is worth pausing on. A large model might have hundreds of billions of parameters. Training it requires processing trillions of words drawn from books, websites, code repositories, scientific papers. The compute cost can reach tens of millions of dollars for a single training run. This isn't a software product that was programmed by hand, it's a function that was found through an enormous automated search. One thing researchers discovered, empirically rather than theoretically, is that scale follows predictable laws. Larger models trained on more data with more compute reliably produce better results. This held across several orders of magnitude. The relationship between scale and capability turned out to be surprisingly regular. That finding shaped the entire trajectory of AI investment over the past 5 years. To get a sense of the scale involved, if you read 1 book a week for your entire life, you'd accumulate perhaps 3,000 books, roughly 1 billion words. A large language model processes that same volume of text every few minutes during training. The gap between how a person acquires knowledge and how a model is trained isn't a difference of degree, it's a different kind of process. Human learning is slow, selective, and grounded in lived experience. Training is fast, indiscriminate, and driven entirely by error reduction. What emerges from pre-training, the initial phase where the model learns from a broad data corpus, is sometimes called a base model. A base model is not particularly useful on its own. It has learned to predict text but it doesn't follow instructions, it doesn't try to be helpful, and it doesn't refuse harmful requests. It just predicts. To make a base model into something like ChatGPT, a second phase of training is applied. Fine-tuning on curated examples of helpful conversations shifts the model's behavior. And a technique called reinforcement learning from human feedback, RLHF, takes this further. Human evaluators rate the model's responses, and the model is trained to produce outputs that humans rate more highly. This is what installs the conversational, helpful character that users experience. The underlying weights are still numbers found by minimizing a loss function, but the loss function now reflects human preference rather than raw text prediction. The result of RLHF is sometimes misread. The model hasn't learned what's genuinely helpful or harmful. It's learned to produce outputs that resemble what human evaluators rated highly. When those evaluators consistently preferred responses that were polite, structured, and confident sounding, those patterns got reinforced. That's useful. It's why these models are pleasant to interact with. It also introduces a specific failure mode. The model learns to sound helpful even when the underlying pattern is weak, and to project confidence regardless of whether the answer is well-grounded. Training adjusts weights to minimize prediction error on training data. It doesn't check whether facts are true. The process has no concept of true or false, only what reduces the loss. A model trained on incorrect text learns incorrect patterns just as efficiently as it learns correct ones. If a claim appears frequently and consistently in the training data, the model will learn to reproduce it. If it appears rarely or inconsistently, the model will be uncertain. Factual accuracy is a downstream consequence of what the training data contained, not a property the training process itself guarantees. This is the structural cause of hallucination. When a model generates a confident wrong answer, it's not making a reasoning error in the way a person might. It's producing output consistent with the patterns its weights encode. Patterns that were learned from text that may have been incomplete, inconsistent, or wrong. There is a second limit that matters practically. After training, the weights are fixed. The model doesn't continue learning from your conversations. Each time you open a new conversation, you're interacting with the same trained state. The model has no memory of previous sessions unless you explicitly provide that context. New facts that emerged after training ended aren't in the weights. The knowledge is frozen at whatever point the training data was collected. This distinction matters when evaluating AI output. The question isn't whether the model is reasoning carefully in the moment. It's whether the training data contained enough examples of this kind of problem for the weights to encode a reliable pattern. A model can answer questions about 19th century history with apparent confidence, not because it reasoned through the answer, but because it saw enough 19th century history in its training corpus to have encoded a strong pattern. When that pattern doesn't exist, when the training data was sparse or contradictory, the model still produces output. But that output isn't grounded in the same way. A trained AI model is a set of billions of numbers found through a mechanical optimization process that encode patterns from an enormous amount of human-generated text. The result is genuinely remarkable. A function that can answer questions, write code, explain concepts, and translate languages without being explicitly programmed to do any of those things. But the training process itself has no access to truth. It has access to error signals and gradient updates. What it produces is a function that's good at predicting text written by humans, which, given how much humans write about the world, ends up capturing a great deal about the world. The gaps and errors in that text become the gaps and errors in the model. Understanding training doesn't make these tools less useful. It makes you better at knowing which tasks to trust them with, which outputs to verify, and which questions to check against a real source. A tool you understand is a tool you can use well. If that kind of precise look at how AI actually works is useful to you, subscribing is how you get more of it.